In terms of real solutions to a quadratic equation, there can be 2, 1, or 0 such solutions. In this video, we look at examples of quadratics that have no solution. Let's start with an example. Can this quadratic function be used to model the area of this rectangle? Y equals negative 2x squared plus 3x minus 15. If not, what modifications would you make to the function? If this quadratic models the area of a rectangle, then it should be possible to write it as the product of two linear binomials, each representing the measurements of length and width. Let's start by graphing the quadratic function, as shown here. Notice that not only does the graph not intersect the x-axis, all y values are negative. So this function cannot be expressed as the product of two linear binomials, and therefore can't be used to model the area of a rectangle. Also notice that all the y values are negative, and since area can't have a negative value, this is another reason this quadratic can't be used to model the area of the rectangle. The minimum value for this function is where the graph intersects the x-axis at least once. This graph shows a single intersection point at the x-axis, and this is because we added a constant term of 13.865 to the original function. This function can be used to find the non-zero values for the area of a rectangle, and because it intersects the x-axis, can be expressed as the product of linear binomial terms. Let's look at another example. Does this quadratic function model the area of this circle? Y equals pi times the quantity x plus 4 squared plus 5. If not, what modifications would you make to the function? As before, let's take a look at the graph of the function. As you can see, this function doesn't intersect the x-axis. It can't be written as the product of linear binomials, so there are no real roots to the quadratic. Furthermore, although the y values of the graph are always positive, the x values are negative up to the y-intercept. One of the simplest adjustments to make to the function is to remove the plus 5 term, leaving a perfect square. This quadratic has a root of negative 4. All positive values of x that result in a positive area are greater than 0. Also, the minimum area for this circle is 16 pi. Let's look at a final example. Can this function be the model for the area of this parallelogram? A equals negative x times the quantity 2x minus 3 minus 25. If not, what adjustments can be made to the function? The area of a parallelogram is the product of the base and height as shown here. Can we model this quadratic as the product of two binomials? Let's first expand and simplify the quadratic to get this quadratic function in simplest form. From here, let's analyze the discriminant. Take the a, b, and c values and plug them into the formula. The b value of 3 goes here. The a value of negative 2 goes here. The c value of negative 25 goes here. Simplify to get negative 191, which means that this quadratic has no real roots. As you've seen from the other examples, that means that the graph is either above or below the x-axis without intersecting it. If we change the constant term from a negative 25 to a positive 25, we get two real solutions, as shown in the graph. However, only the solution with a positive x value works. Also, notice that the only values for y that are acceptable for area are in this range of values.